Welcome to GWA Physics, and I just wondered what you were all up to tonight. Thought you might be reviewing for the test, and I thought I'd try to make things a little easier for you. So I'm going to work a couple of these problems from the review sheet on the video. So let's get started. Let's see here, we'll start with blue. Let's start with number 4. On number 4, they have a problem that starts out with a spring here like this. It has a block that's being pushed against the spring, and it's a 2 kilogram block. The K value is 320, and the force exerted on the block is 80 newtons. Now, after this block comes off the spring, it's going to come out here and there's going to be a section of friction. And that's going to be 3 meters long right here. And it's got a coefficient of friction equal to 0.15. And they're asking what is the work done by the friction here. And they're asking after that, what is the velocity of the block after it comes across the friction. So let's draw one more block right here like that, and we'll be ready to get started. Now, one of the things that's important for you to see is that in a problem like this, like all the problems on the review sheet, there's a conservation of energy. So when we push against this block and push it into the spring, it's going to compress, it's going to get shorter, okay? And when it gets shorter, there's going to be a certain amount of potential energy that's stored in the spring. When we let go of the block, then the spring's going to push the block that way, and all the energy that's in the block, in the spring, is going to be transferred to the block. And now the block is going to be moving this way with a certain amount of kinetic energy. Now, the spring's energy is converted into the kinetic energy of the block, and then the work done by friction, the friction is going to take away a portion of this kinetic energy. But you can see from the problem that they want to know how fast it's moving over here, which means it probably hasn't taken away all the energy yet. So let's go through this problem step by step. And again, I think the hardest part might be right here where we're dealing with the springs. So you've got a force and you've got a K. There's 2 equations. One of them is F equals Kx. And the other one is the potential energy is equal to 1/2 of Kx squared. Now, with the information that we start with, it's got a force and it's got a K value. So it looks like we have to start here. Let me change colors right quick and see if this will stand out any better. So we've got 80 right here, 80 newtons is equal to 320 x. So we're going to solve for x, and x comes out to be 0.25. And the units for x is meters. So we're going to immediately substitute that down here into the next formula because we're interested in the amount of energy. So we've got 0.25 squared, and half of K, well, half of 320 is 160. And so when we do that, we're going to get the total amount of energy stored in the spring. And the answer happens to come out to 10 joules. 160 times 0.25 squared is 10 joules. So the spring has 10 joules of energy in it. But then you should remember that I said that the energy that the spring has is going to be transferred to the block. So as this block starts sliding this way, it has 10 joules of energy also. So they want to know in the problem, what is the velocity of the block just before it goes across the friction? Well, the kinetic energy of the block is equal to 1/2 of mv squared. So we've got 10 joules is equal to half of 2, which is 1v squared. And really the 1's not necessary. So we take the square root of both sides, and v ends up being 3.16, and that's meters per second. The next thing we're interested in is how much work is done by the friction. Well, the formula for that is that the work done is equal to the coefficient times the normal force times the distance. Well, we have a good bit of that information already right there in front of us. We've got the coefficient of friction at 0.15 right there. We've got the distance across the friction as being 3. So the only thing that's even remotely challenging might be to solve for the normal force. You're supposed to remember that the normal force is equal to the weight, which is F of G, and F of G is equal to M times G. So we're taking 2 times G, which is 10, or the value is 20 total. So we got 0.15 times 20 times 3, and that comes out to 9 joules. Well, look at what we've got. We've got a box that was sliding across the counter, and it had 10 joules of energy. We just lost 9 joules because we slid across the friction. So this box only has 1 joule of energy left. If we take that to be 1/2 of mv squared, again, if this was 2, then that would just be 1v squared is equal to 1, and the square root of 1 is just 1 meter per second. So at the end of this problem, the velocity of this block is moving ever so slowly at 1 meter per second across the counter because it lost 9 joules of energy due to the friction. Now, I hope this will be a big help. That's one of the problems that's on the review sheet. You'll have to be able to solve stuff using springs, and you'll have to be able to use stuff where you're solving for the friction. So study up on that because it's going to be on the test. Have a great night.